Okay, so let me first briefly introduce Dr. Chen Qin, who is a lecturer in computer vision and machine learning at University of Edinburgh. And before that, she obtained her PhD in computing research from Imperial College London and her MSc from Tsinghua University. Her research is about artificial intelligence, especially with application with using deep neural network to medical imaging. And she has published many papers. And today we are lucky to have her here to present her current works in using deep learning to solve medical imaging problems. Without any further ado, I will hand this talk to you, Chen.
Yeah,
off you go.
Thanks, Jimmy, for the introduction. So I'm very happy to introduce our recent work to you. So I'll be talking about deep learning in medical imaging. As you see from the title, we'll cover a few aspects from the signals to also the clinical use information. Yeah, so deep learning in healthcare has raised a lot of interest in recent years. So if we see from the headlines of the newspapers and magazines, we'll see there are a lot of excitement in this area and emerge that can detect the coronavirus in seconds. And especially in RNN, we also see that artificial intelligence is the winner of this RNN 2020. So when we're talking about deep learning in medical imaging, people might have the first thing that it's all about the classifications, where we classify the tissues as normal or abnormal. But in fact, we'll see that machine learning can actually help to improve the entire medical imaging workflow, from the image acquisitions, reconstructions, to the disease diagnosis and the treatment. So we will see that the machine learning and deep learning will play a key role in this improving this workflow. So I will introduce my talk from the three aspects. So I will first introduce the deep learning for the inverse problems with a particular application for image reconstruction. And we will also see some of the applications where we can extract some clinical useful information via this medical image analysis, such as segmentation and registration. And finally, if we still have time, I would like to introduce some of the integrated applications for this reconstruction and analysis. Yeah, so let's take a look at the first part. Well, we know that the MR data acquisition is inherently slow due to both the hardware and physiological constraints. So given the signals in K-space, so if you are not familiar with MRI data, so the raw data of the MRI is acquired in this K-space. And after this Fourier transform, we will then see the images in this image space. Well, because the acquisition process is very slow, for instance, if we are imaging a cardiac data, the heart data, it might take like 30 to 45 minutes here. So to accelerate this process, most methods will acquire a fraction of these data to accelerate the process. We see here that, let me see if I can use this notions. Can you possibly see my cursor here? Let me try.
Yes, I can.
Yeah, so if you see, yeah, great. Yeah, so if you can see this, if we undersample the data in K-space, we'll see that the signals in this signal space will be very aliased because they violate the Nyquist sampling strategy. So what we want to do is, if we can reconstruct the signal from this alias space back to this original fully sampling space. Well, traditional methods, we use these compressing approaches, and today I'll be focusing on talking more about these learning-based reconstructions. Yeah, but let's first review about these formulations of this inverse problem. So given an observation Y in K-space, we would like to reconstruct the image X. So the compressed sensing formulation can be formulated as this, which consists of a data fidelity term. That is to ensure that when the reconstructed data is transformed back, undersampled transformed back to this original K-space, we would like to preserve the data that we have acquired. And most commonly, we also have some assumptions on the data, which is called regularization terms, such as some of the sparsity or smoothness in some of the transform domain. Well, to solve this problem, to solve these objective functions, we will introduce the auxiliary variable Z and then relax this problem to unconstrained optimization via this penalty method. And then we can solve this equation via this alternative minimizations. Then we can decompose the problem to these two sub-equations where we will update the intervariable Z and this X iteratively. So we'll see that the first equation can be viewed as a denoiser. We're given this objective, we're given the image X at the I step, we will denoise the image to Z. And then the second equation will be a data consistency term where it keeps this data fidelity here, and then we will update the Z back to this X in this image domain. So how can we formulate this in a deep learning framework? So as I mentioned, like the first equation refers to a denoiser, then naturally we can use deep neural networks to formulate the first equation here. So that we use a deep neural network to using it as a sort of a regularization to learn from this X to this Z here. And then the second equation, we can see that can give us a closed form solution that we can explicitly embed it into a deep neural network with a data consistency layer here. Then we will see this process of this reconstruction then can be viewed as iterative projections between the manifold of these plausible images and manifold of the data consistency steps. And since we always incorporate the raw data, this Y here, into this learning processes, so some group of these methods also call such kind of methods as the physics-informed learning. So based on these deep learning formulations, here we would like to first address a problem for the dynamic MR image reconstruction. So in terms of the dynamic MR image reconstruction, we know that the data of this will be a sequence of MR data, so that we will see a sequence of the data with the same region of interest, like the heart we have here, that to beating in cardiac cycles. So that's the sequential data. And then from previous slides, we know that it's also iterative projections between these manifolds, that we can also view such iterations as another type of the sequential steps. So motivated by these two, here we propose to employ this recurrent neural networks to let it to evolve over both of the iterations and time, that is to embed this iterative optimization process in a learning setting, as well as to exploit the spatial temporal redundancies along the temporal sequential steps. And particularly, we see from this left diagram that we have a similar form as what we just introduced in the deep learning formulations, where we'll have a deep neural network as a denoiser and a data consistent step. And specifically in the CRNN here, we have a CRNI unit. That is what we mentioned as this first bullet point here, that to embed this iterative optimization in a learning setting. That is to say, we have these hidden-to-hidden connections along these iterations. So if we unfold this across iterations, we'll see such hidden-to-hidden connections along these iteration steps, which allow the information that is learned from the previous steps to be effectively propagated to these future ones. And additionally, to exploit these spatial temporal redundancies, we further have a bidirectional convolutional recurrent neural network that evolves over both the time and the iterations. And particularly here, we have these red arrows here that indicates the bidirectional connections between the neighboring timeframes that allows information to propagate such informations more efficiently along the temporal sequences. And to note here, this will also be the first work that using this RNNs on this dynamic MRI reconstruction. We have compared our work with some of the other approaches, such as the traditional compressed sensing method, like KT-SLR or KT-focus, and some of its counterparts like 3D CNNs with shared neural net and also unshared networks here. And by comparing our results with the other competing methods, we can see that the proposed method can achieve visually better reconstructions and also quantitatively smaller errors, especially around the region of this interest. And in terms of this PSNR and the reconstruction speed, we will also see the proposed method can achieve a better reconstruction performance with faster reconstruction speed and a fewer number of these parameters. So what I have just introduced were mostly based on exploiting such dependencies in this image domain. And in fact, in this problem, we can also exploit the spatial temporal redundancies in some transform domains. For instance, here we propose a method that to exploit these spatial temporal correlations in this XF domain. So for some of you who might not be familiar with this, so the XF domain is a Fourier transform from this KT domain, that the K space along the time. And if we do a Fourier sampling of this, we will see that signals in the XF space will be very sparse. But if we undersample the signal, that also presents such aliasing artifacts. Mostly exploit such sparsity in this XF domain. And motivated by this, here we would also like to propose a deep neural network that can exploit such redundancies in both of these XF and image domains. And particularly here in the figure here, we propose an XF CNN that tries to reconstruct the signals in this XF domain. And then they just introduced that to reconstruct the signals in the image domain. And then this reconstruction process can be iteratively updated by alternating between both the XF and this image spaces. And by exploiting such information in this complementary domain, we can see that our method can achieve better results in comparison to a single domain reconstruction, such as its counterpart, the RNN-MRI, and some of the advanced like data sharing methods in the CRNNs. So what I have just introduced was still based on some of the simulated setting where we assume that the data was acquired in a single core acquisition. But in practice, the parallel imaging is more frequently used to accelerate the MRI acquisition clinical practice. And the parallel imaging works by acquiring a reduced amount of this K space with an array of these receiver coils. And specifically, we see from this compressed sensing-based parallel MRI model based on sense, we will also have a similar form of objective functions, but different with a single core acquisition. We will have another variable here that is SI, which represents the ith coil of sensitivity map that is used, as you see from here, that is used to assess the spatial localizations of the MR signals. So the question is, can we possibly extend our deep learning framework in a parallel imaging setting to address more clinical, meaningful scenarios? And to address this problem, here we propose another framework that is called complementary time frequency domain networks for this dynamic parallel MRI reconstruction. And the problem can be similarly formulated as such, where we still have a data fidelity term, and we will have some of the regularizations in both the XIT domain and the XF domain, as I just introduced from the previous work. And to solve these equations, we can similarly introduce these variable splitting techniques by introducing some auxiliary variables, such as this U here, U, rho, and sigma I here, that is to decouple this, this data fidelity term with these regularization terms. And by using alternating minimizations, we can also alternate between these different variables here. So if you take a close look at these equations, actually the first equation is corresponding to a denoising, as what we mentioned, in this XF domain. And the second equation will be also denoising the image domain. And the third and the fourth equation actually can produce a closed form solutions, where the third equation is a coil-wise data consistency. We see the data fidelity term here, and it's for each coil separately. And then the last term, if we solve that, we will see that it's a weighted combination of this U, rho, and the sigma I here. So based on this, we would also like to formulate that in a deep learning framework for this reconstruction. And here, as I mentioned, we will have this XF CRN for these XF domain reconstructions, and we have XT CRN for the XT domain reconstructions. And then this is followed by the coil-wise data consistency, as indicated in the C block here, and a weighted coupling of the previous reconstructions of these different domains here, that to reconstruct our final reconstructions. So you see that the network can be trained by giving undersampled data, and we predict the reconstructions, and the supervision comes from like L1 loss between the reconstructed image and the fully sampled data. Compare our method with some of the state-of-the-art approaches, like the cascade CRNN in deep learning and some of the dynamic VN, as well as compressed sensing approaches of this KT SLR. So by comparing with these, we can see that the method can produce fewer errors around these dynamic regions, and it will produce visually better reconstructions in this region of interest as well. And then we also investigate how the method can generalize to data from another scanner. So basically, we train our model from one scanner, and then we take the model and test it on the data from another scanner. And we see that in the new scanner, the data from the new scanner, we can still see a reasonably reconstructed results on these different undersampling factors. Even we can push that to 24 undersamples because of the dynamic, because of the parallel imaging. And also, if we perform that, the acceleration factor that above 16, we can actually realize a single breath hold 2D cine acquisition, which can largely facilitate the acquisition speed of this MRI for single breath hold. Right, so we know that the deep learning is mostly data hungry. So there have been many efforts that to push the development of the method in accelerating MRI imaging with AI. So we know there's one challenge, which is called fast MRI, that provides a large number of data, either on the near MRI or the neural MRI, which can help us to develop methods and to validate our approaches based on these large databases. And we, as a group, advised with Jiming that participated in this challenge in 2019, and our team wholly case-based ranked second among all these participants. We recently have an RNN paper that to systematically evaluate these deep neural networks on this data. So if you're interested, please also have a check of this. Yeah, so this is first part of this work that is on the image reconstruction. So if you have any questions, I can take some questions now, or if not, I can also continue the second part. We can do a question at the end.
I think we can move forward directly.
Are there maybe already some questions? Okay, great. Yeah. So from the image reconstruction, I would also like to talk about this image analysis part. So the image analysis will be like some of the segmentation, motion tracking, and the registrations. So the first application, the first work I would like to introduce is about this joint image segmentation and motion tracking. So for the cardiac image segmentation, we know the region of interest will be the ventricles part of this. And of course, that will also be the regions that where the motion exists. So we can assume that these two tasks, the segment, are closely related and can provide complementary information. And of course, if we perform these two tasks separately, there are a few challenges here. So if we work on segmentations, so commonly we will have only the diagnostic and asystolic frames that are annotated, which means given a sequence of images which have 50 frames, we probably can only have 2 frames that are annotated. And then for the motion field, there's no ground truth available for this because the dense displacement will be very difficult to obtain. So how to tackle these challenges? Here we propose a method that is beyond supervised learning that consists of a self-supervised motion estimation plus a weakly supervised segmentation. And specifically, we can take a look at this joint framework. It's a motion estimation branch. And second part will be a segmentation branch. So for the motion estimation branch, it consists of few components like the cine encoders that will extract information and followed by a multi-skill concatenations of these feature maps. And then because we are processing these temporal sequences, here we also have an RNN here that to propagate information along the temporal axis. And then this is followed by a 2D displacement field, which represent the displacement along both the x and y axis. That is what we would like to obtain for the displacement. So to train this network, as we mentioned, we don't have ground truth for this. So we have to rely on some of the self-supervision here. That we use this image similarity as a self-supervision, where we would like to measure the dissimilarity between the target image as well as the warped source image. That's between the fixed image and the warped moving image, basically, of these intensities. And then because this is an inverse problem, so we need to have some of the regularizations on the deformation fields to make sure that the solution is unique. So here we would like to take a first order smoothness on the deformation fields to constrain this displacement estimated. And then for the second branch, the large amount of those annotated data. So as we mentioned, only 2 frames out of 50 that are utilized. What about those large number of unlabeled ones? Here we would like to propose a solution by coupling the segmentation branch with this motion estimation branch via this multitasking. And particularly, we would like to share the feature encoders with the Siamese feature encoder in this motion estimation branch to form a triplet feature encoder that can utilize those information that learn from those unlabeled data from this motion estimation branch to inform in the segmentation branch. And then secondly, we see there is also a link between this displacement with the segmentation. So here particularly, we see that by using this displacement, we can warp the segmentation where we won't have, where we have the labeled data to the frames that we don't know about the labels. And then we can use such, sorry, I think I'm saying the other way. So we warp the segmentation that are unlabeled to the segmentation that are labeled, and then we can form a supervision loss, LW here, that is on those unlabeled data. And of course, we have this labeled data, so we can also form a segmentation loss on labeled data here. And then this whole network can be trained by this composite loss by weighting between the segmentations and this motion estimation losses. So now, giving a sequence of these images, we can now estimate the segmentations and the displacement simultaneously on these cardiac frames as indicated here. Well, we validate our methods on this large-scale imaging data. So we evaluated on this UK Bellbank dataset, which consists nearly 5,000 subjects, and we divided them into the training, testing, and validations. And here we see that by comparing with segmentation-only methods, our proposed method can achieve better results compared to a single segmentation framework. And then comparing with some of the conventional motion tracking methods, our proposed motion tracking method can also achieve a reasonably better performance with a smoother and accurate estimation. So the motion tracking is actually an application for the image registration. We know the image registration is also an ill-posed inverse problem that can be formulated in this objective function, which consists of an image dissimilarity measure and also a regularization term, as we just introduced in the motion trackings. And to solve this, as we mentioned, to make sure that this inverse problem has a unique solution, we need to add some of the assumptions and regularizations on this solution space. So most methods will impose some of the smoothness on the deformation field, also some of the other properties such as invertibility and some of the volume preservations. Or we could also constrain this transformation with some like feasible transformation like freeform deformations or spline transformation, etc. So even though these regularization generic, there is often a lack of application-specific prior knowledge on the particular applications. So we would like to work on these motion tracking applications. So could we possibly incorporate some of the prior knowledge on the modeling of the heart, such as the biomechanical information about the heart motions into this registration framework? So this motivates us to propose such a biomechanics-informed neural network for myocardial motion tracking. And particularly, the framework consists of 3 parts. So the first part, we would like to first simulate a set of biomechanical simulations based on the biomechanics that we are aware with, that is governed by these 2 PDE. So the first equation describes the elastic properties, and the second equation ensures this incompressibilities of these motions. And then based on these simulations, could we possibly learn such a behavior that we would like to expect from these biomechanical simulations? in a data-driven way? And the answer is yes. So we would like to learn such a prior knowledge based on these variational autoencoders, where we would like to reconstruct the first order derivatives of the deformation by using these variational autoencoders, so that to ensure that the deformations can lie on the manifold of this VAE that is represented by the latent vectors of this Z here. And particularly the VAE reconstruction loss is a losses of this, to minimize this reconstruction loss of the first derivative, as well as the KL loss of these distances here. And then given that we learn such behaviors, so we assume that we have learned these biomechanical behaviors of these VAEs, then we can couple it with any of these registration network that we have in deep learnings, right? So here we have the registration network, and then we can simply couple this VAE losses with a standard, the final losses for this training of this registration network. So what we have this registration network here is what we just introduced in this motion trackings. We have these VAE regularizations that we ensure that the estimate deformation fields can fall on the manifold that is represented by the learned VAEs here. And to validate this method, we evaluate them in terms of this registration accuracies and the volume preservations. That is the tissue incompressibilities that we have simulated from the biomechanical simulations. We see that our proposed method can achieve a good balance between this registration accuracy and the tissue incompressibilities with a similar range of this Jacobian -1 with a higher dice of this die scores in terms for this registration accuracies. And in particular, from the visualization, we will see here we visualize the log of Jacobian determinant. So a bit more context on this, the Jacobian determinant, if it equals to 1, which would indicate that the tissue incompressibility, which is the desired property that we want to have, and the log of Jacobian determinant if equal to 0, which means that it preserves these volumes here. So we can see that proposed method can have a better preservation of these volumes around these myocardial regions. And again, we by using these estimate deformations, we would also like to evaluate in terms of this myocardial strain, and we compare that with the reference values that we have obtained from this tagged MRI. And we see by comparing from the other approaches, our method can achieve a better values of this myocardial strain, which can be useful in clinical practice. Yeah. So for the motion tracking, we see that we are working on the same modalities, basically the same sequence of this cardiac. So that's a mono-modal image registration. So what about for the cases of this multi-modal image registration? So multi-modal image registration is challenging than the mono-modal registration because we can't really find these intensity relationships between these different modalities. And there could also be some ambiguous regions in different modalities. So how could we possibly address such kind of things? Well, of course, there are two approaches here, and I will take some representative work to introduce to you. So the first one, as I show here, is that we would like to transform this multi-modal deformation to a mono-modal deformation via this image disentanglement. And particularly here, we would like to disentangle the images into a domain-invariant latent shape representation and a modality-specific appearance code. Since these two subjects represent the same subject, so once they have embedded into a latent shape representations, then we can transform such a registration, multi-modal registration, to a monomodal registration here in this latent shape space. And specifically, what we do here is we leverage the method from the ECCV and ECCV in 2018 that use some of the disentangle representations. Here, we would like to disentangle our images into a shape representations as well as appearance code here. So we see that once we have embedded these images into a common latent shape representations, the registration will then to learn a transformation that can minimize the distances between these 2 points in the latent space, which forms a latent similarity here. So we use such a latent similarity as sort of supervision, a self-supervision to learn this registration problem in this latent space. Well, in some of the cases that there might be some ambiguous regions which can't be identified in this latent space, we additionally propose another metric, that's a learning-based similarity metric based on the discriminators. So here what we have is that we would like to learn this transformation, this delta here, by using discriminator to discriminate whether these 2 pair of images are well aligned or not. So we have a well-aligned pair, which is as a real pair, and we have this warped and fixed pairs as a fake pair. So then the discriminator would learn a metric, would learn a similarity metric to discriminate between these 2 pairs, and then to enable this generator, that's what we call it a registration network, to learn a deformation field that can fool this discriminator to make them well aligned. And then we combine these 2 latent similarities, combine the latent similarity and the learning-based similarity metric that can provide us with complementary information. So this is a work that we actually reduce the multimodal to a monomodal problem, but in fact, we can also deal that directly by using some alternative similarity functions, similarity metrics. So more recently, we have a work that is mutual information-based deep image registration, where instead of using the intensity mean squared errors as in monomodal registration, here we exploit this mutual information here as a multimodal similarity functions that to self-supervise this alignment here. And particularly, we make such mutual information differentiable and can be trained end-to-end by using a deep neural networks here. So if you're interested, please have a check of this work that is in middle this year. Yep. So that's some of the work that we have that in extracting clinical useful information via some of the segmentation and registration tasks. And finally, let me see. Yeah, I think I can briefly introduce some of the integrated applications of these 2, of this reconstruction and analysis. So one of the applications is about the motion compensated dynamic MRI reconstruction, where we can actually exploit this motion information explicitly in a reconstruction network. So here we like to exploit such motion compensation scheme along the temporal axis and then propagate the K-space data along the temporal profiles to reconstruct the MRI data. And particularly if we extremely undersample the data, we can see that the proposed method can achieve a better results in comparison to some of the state-of-the-art approaches. And some of the other work includes like the direct analysis from this undersampled MRI. So in most of the processing pipeline, we would first to reconstruct the images, and then we analyze those images to extract some useful information. But can we possibly bypass this reconstruction stage and directly estimate the information that we would like to have? So here we had a work that to extract directly from this case-based data of some of these parameters that we would have. For instance, you can see from this figure that when sampling only even one line case-based, we can have a prediction that is very close to the ground truth data in terms of the segmentations. Direct analysis on the joint segmentation also extract accurately of these clinical relevant measures such as ejection fraction errors is very small, even though we employ such a high accelerated data. So these indicate a great potential in facilitating this MRI reconstruction and analysis for the future intelligent MRI imaging. Yeah, so to summarize, we see that deep learning or machine learning plays a crucial role in medical imaging, both for this image acquisition, reconstruction, and image quantification analysis. And deep learning will have the capability to transform this image, a huge potential for the future of this MRI imaging analysis. And of course, to build an AI for clinical application, we certainly require this close collaboration from the different parts, computing, engineering, and clinicians. So most of our work that I've introduced have been open source and published. So feel free to have a check if you're interested, and feel free to get in touch if you have any questions. Yeah, and finally, a small ask here that we are hiring PhDs in similar topics, and we have several ways to apply to work with us, like from the School of Engineering, the Biomedical AI, CDT, and some of the advanced care research centers. So if you're interested, feel free to drop me an email. Okay, great. So I'm happy to take some of the questions that you may have.
Okay, thank you. Thanks, Chen, for the nice talk. I'm wondering if there is any question from audience, and you can unmute yourself directly asking her. Okay, Costa, you have any question, Costa?
Yes, I'm typing slowly apparently. Let me raise it. So, hi, Chen. Question is, out of your whole experience with reconstruction, so you've been working a lot on reconstruction from different aspects, what do you think are the most problematic, the unsolved problems? So reconstruction achieves great results in a lot of settings. What do you think are the most important open problems?
Yeah, I think the problem now is that we need to work in a more clinical scenarios. Like most work previously worked only on single core acquisitions, but we don't use single core acquisition anymore in clinical practice. So the thing is that we need to turn to some more clinical scenarios like parallel imaging that is mostly commonly used. And another issue here is that we are still in a stage of working mostly on those retrospectively undersampled data, where we actually simulated those undersampled data, and then we evaluated on some of the retrospective undersampling data. So it would be important to see how our method that is trained on this data, how they can perform in some of the real scenarios, such as in some of the prospective acquired data. So I will see this as an important question here, which will also be an important step towards applying this method in some of the real practices. And besides, of course, there are some open questions as in some of the other deep learning tasks, like the generalizations. If we train our methods on healthy data, can the model reconstruct? This is also something of interest. And if the network can can produce reliable reconstructions, like if it can fail at some regions, and can it still give us a signal of this? Can we trust images? Yeah, I think these are also open questions in terms of all these like medical imaging applications.
Thanks. Just very short follow-up. I'm not aware, I'm not following too close reconstruction, but you probably will know. Do you know if deep learning was applied in practice nowadays for reconstruction in any like products by any company and this kind of stuff? So segmentation, for example, reaches tens, you start seeing the first products, but segmentation has a different thing that is like, it helps interpret the image. Well, reconstruction is, it changes immediately the image that you're seeing, right? So if perhaps it's a little bit scary to depend on deep learning for showing it to clinicians. I was really wondering if it is already in products.
Yeah, right. So I see recently, like Philips got an FDA for their products of reconstructing, for the reconstruction deep learning. But I would say the most commonly used methods are even not compressed sensing yet. So compressed sensing only got FDA maybe in 2017. It's still very not very far. It's so mostly compact is still parallel imaging, I would say.
I see. Thanks a lot.
Yeah, thank you.
Okay, any other questions? Thanks, Costa.
Hello, can you hear me? I had a question about the compressed sensing part as well. Sorry, but you said that the deep learning models were built on top and use the model-based methods as inspiration. I was wondering, like, how did they compare to if you solved the inverse problems iteratively in terms of, say, robustness and accuracy? Because I assume they're quicker at inference time, but then how do they compare in other aspects?
Yeah, sorry, I think I had a bit of connection problem just now. So may I check if your question is how does the deep learning compare with the compressed sensing, and what's the advantage of the deep learnings? Is this what you're asking?
Yes, that was it.
Yeah, great. So as you mentioned, the fast inference is actually one big advantage of deep learning over the compressed sensing method, where compressed sensing would like iteratively update the gradients and to optimize the functions would take quite a long time, especially in large data set, especially in dynamic data where we have a sequence of these images. So the fast inference is a big is a good part of this. And apart from that, so we know compressed sensing works only on one pair of these images. It can't really take advantage of the information that is contained in most of the scan that we have been acquired in clinical practice. So we have a large cohort of the data that can actually be utilized, but those were not exploited in comparison by using compressed sensing approaches. But in contrast, the deep learning can utilize such kind of this data and exploiting those assumptions in all these scans and utilize such information to reconstruct the data. So basically we see that it uses more data and it can learn such of the prior knowledge from these large scans, which can't be exploited from these compressed sensing methods. Yeah.
Okay, thank you.
Does this address your concern?
Yes, thank you.
Thank you.
Maybe following Joe's question, you mentioned this. I mean, do you mean supervised setting, right? If you do it on the unsupervised, because iterative methods are unsupervised methods, right? We don't need training data. We don't need ground truth, right? Do you think? I mean, if we do unsupervised learning for MRI recon, do you think still can do better than traditional method, iterative method especially, for example?
Yeah, this is a good point. So currently we are mostly at the stage of this supervised learnings. I guess that also depends on how we will formulate such unsupervised methods, right? So yeah, I guess another good benefit in deep learning is that it can give us a good parameterizations of these regularizers that we might learn from those data. So in processing, we probably just assume some form of sparsities and
yeah. I mean, you can learn regularizer. You can learn regularization because you have ground truth, right? Otherwise, you still need to design it by hand, right, by yourself. I mean, because you have data, it's data driven, right? It's you don't need prior knowledge because all prior knowledge in this training is your ground truth, right? And why, if you don't have any ground truth, you might still need a regularization term, right? In that case,
yes,
I mean, under unsupervised setting, I'm not sure if it can actually do better, to be honest. And the reason why
this is the reason I mean, this is a good point.
Okay, sorry, carry on.
Right. Yes. So I guess this also depends on how you design such unsupervised method, right? Even though it's unsupervised, we could probably still utilize those large number of data that is available, and we could still explore some of these properties that exist in this data. Like some of for instance, in dynamic data, we have a data redundancies. Even with unsupervised method, we can still exploit such correlations along the temporal axis that could learn somehow from the data about such kind of regularizations as well.
Yeah, the reason why I ask this.
Yeah, but I agree that a challenging.
Can you hear me?
Yeah,
hello?
Please go ahead.
Oh yes. I think why I mentioned unsupervised training, because in image registration, which also in your slides, right? And for image registration, it's indeed unsupervised learning, right? And we compared. We actually had some work comparing this unsupervised learning with this iterative methods. Actually, it's not actually doing better than iterative methods without any, ground truth, right? Especially for image registration, because we have no ground truth. We can't find any deformation grades, right, to supervise the training. Therefore, in that scenario, we actually proved in one of our papers recently, it's still not outperform traditional method or iterative method. So how do you what's your opinion on this type of problems?
Yeah, I agree with you on this. So we often see that even though now it's deep learning registration, can actually achieve competitive performance, not really outperforming these iterative methods. But here, I think a good thing is that we can actually do more things here. Like what I show about this biomechanics-informed, we can learn some sort of prior by using some data-driven approaches. That's deep learning, but we can also still use combine that with such iterative optimizations.
Okay, good. Thank you. Any other questions from audience?
Do you agree with me? If you say this, I agree.
I think we have some connection problem, Chen.
Yeah, I guess, yes, we have some delay.
Yeah, I agree. So it's my network might be more flexible in this setup, especially in deep learning, right? I can use masks, segmentations, or et cetera, information to train a better network, while iterative methods might be more like rigid, right? It's not easy to adapt to different scenarios. In that case, I agree. Deep learning is more flexible in this unsupervised setting. Okay, so is there any other question from audience? Maybe someone else want to have some other questions. Okay, I think sorry, if there is no a further question, I have a few, like 1 or 2 questions. So especially for imagery registration. So if you for the cine MRI images, right, you register ED to ES, or you register between each intermediate frames? Okay, I see a chat here. Okay, yeah. So can you hear me, Chen?
Yes, I can hear you. Yeah.
Yeah,
Do you want me to answer your question or?
No other questions at this moment. I think I have a few questions. I mean, yeah.
Yeah. Yeah, so for the evaluations, we register ES to ED because we only have segmentation on these 2 frames. But for the visualizations of these, the dynamic sequences, we certainly register between these different frames.
Yeah, I mean, because the deformation between each 2 consecutive frames are very small, right? I'm not sure if CNN can actually learn such accurate small deformation, right? Because in iterative method, we indeed can find a very accurate deformation, even the displacement is very small. But I'm not sure if CNN can catch it, or what do you think about it?
So here we actually estimate the deformation between those the frames at different time points with ED frame. So the fixed image will be fixed. Yeah, so the reference image is fixed, so that's ED frame. And we register all the other frame to this ED frame. And that is what we show here on the visualizations. In terms of the small deformations, I think the CNNs can predict of these. So I visually checked some of these neighboring frames, which looks fine to me.
Okay, yeah. Excellent. Yeah,